Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 10 on exponential models based on percent growth. That's a pretty lengthy title, but what we're going to be doing in this lesson is we are going to be creating exponential functions if we know how much a particular quantity is growing or even decreasing on a percent basis. So let's get right into it. It's actually pretty easy. Let's do it. Exponential functions based on percent growth. There are many examples in the real world where things grow at a constant percent rate. These types of phenomena can be modeled using exponential functions. So let's kind of get into it in exercise number 1. A population of fruit flies is growing at a constant rate of 6% per hour. The population starts at t equals 0 with 28 flies. Letter A. Using what we learned in the last lesson, determine the population after each of the following amounts of time. Show the calculation you use as repeated multiplication. All right, so let's talk about this, right? What it means to be growing at 6% per hour is if we want to know how much the population is after 1 hour, we're going to take our 28 flies and we're going to increase it by 6%. Now, what we saw in the last lesson is in order to do that, we're going to take 28 and we're going to multiply it by 1.06. All right, that's simple enough. We just need to use our calculator to do that. I think I'm going to clear this thing out. So we've got 28 times 1.06. All right, and that's going to be 29.68, which of course we would probably round to 30. Now, after 2 hours, what we would want to do is we'd want to take the 30, or the 29.68 really, and we'd want to multiply it by 1.06 again. But keep in mind that would be 28 times 1.06 times 1.06. So after 2 hours, what we really have is our original amount that has been increased by 6% twice. Now, watch out, increasing by 6% twice is not increasing by 12%. Percents do not work that way. But think about now how easy this is. After 2 hours, right, we can just do 28 times 1.06 raised to the second, and we're now going to have 31.4608, or just 31, right? Now finally, right, after 3 hours, we're going to be doing 28 times 1.06 to the second, which is 31, times 1.06 again. So effectively what we're going to have after 3 hours is 28 times 1.06 to the third. Hopefully you're already getting a sense for why this would be an exponential function, right? So we've got our 28 times 1.06 raised to the third. A little bit hard to see, 33.348448. Again, the reason I'm rounding here is we're talking about a population of fruit flies, so we can't have a fraction of a fruit fly, even after we swat them, right? And so we get that. Now, the most important thing to note here, right, isn't the final answers of 30, 31, and 33. It's the pattern, right? So after 1 hour, it's 28 times 1.06 to the first. After 2 hours, 28 times 1.06 to the second, 28 times 1.06 to the third, etc. And that leads us beautifully to letter B. Based on A, find a formula that models the population P as a function of the time in hours T. Well, it's simple, right? The population of fruit flies, right? Function notation here, population P of fruit flies is going to be equal to our original amount, 28, times our growth factor, 1.06. Well, it'd be nice to have that, raised to the T. And there it is, right? And that's exactly, of course, what we were doing right here. When t was equal to 1, it was 28 times 1.06 to the first. When t was equal to 2, 28 times 1.06 to the second, etc. And now we can evaluate something like letter C. What is the value of p of 24? All right, that's simple enough. You just need to substitute the 24 into this function. Pause the video now and go ahead and do that. All right, simple enough, right? Here we go. P of 24 is going to be equal to 28 times 1.06 to the 24th. All right, let's see what that is. 28 times 1.06 raised to the 24th. All right, is 113. Rounded to the nearest fruit fly. 113. Again, the reason I'm rounding is that we are talking about a population here. In a population, whether we're talking about fruit flies, people, or llamas, right, the outputs can only be whole numbers. All right, excellent. Let's take a look at letter D. What does the calculation you made in C represent about the fly population? Then state the range of the population function over the domain interval 0 to 24. Okay, great. Well, first things first, what does that 113 tell you, right? And that I might want to kind of look back here. What does the 113 tell you, number one? And two, what would be the range for the domain interval 0 to 24? Pause the video now and see if you can do both of those. All right, well first, what does our answer to letter C tell us? After 24 hours, the population is 113. Now, what is the range? That's a little bit tricky here, right? The range, remember, are the outputs. So what was the output at 0? What was our beginning population? Well, our beginning population, right, was 28, right? So our range is going to go from 28 all the way up to 113. Yes? But that's not an acceptable way to write a set that represents the range. So here we go, right? The range is going to be any integer, and that's key, such that 28 is less than or equal to y, which is less than or equal to 113. If you want to use p of t in there instead, I would encourage you to, but it's also okay to use y. Now, I don't know why I said an ant integer. I'm not sure what an ant integer is. But notice here I said any integer, okay? I didn't say any real number, and I didn't use interval notation. Now, the reason for that is, again, the population itself, right? Those outputs are whole numbers. So if I said every real number, that would say that, well, okay, the population could be, 22, or actually, let me give you a number in this range. It could be 36.8 fruit flies. Well, there aren't going to be 36.8 fruit flies. There just aren't. Anyhow, let's take a look at the graph, letter E. Using your calculator, sketch a graph of the population function for the first 24 hours. Mark the y-intercept. All right, cool. Well, this should be easy enough. Let's put that function in. Let's go over to our grapher. Here's our grapher, f1. So what did we have? To begin with, right, our function was 28 times 1.06 raised to the x. We're going to use these variables instead of t's and p's. That's okay. Actually, sorry, let me do this. Raised to the x, wouldn't have made a difference, enter. All right, now I want to get our window right. So let's see, what does our window look like? In terms of, x, I'll just put -5 for my x min, that doesn't matter. X max 24. Y min, just a little bit of negative there. We'll do -10. Y max, they gave us, was 120. I won't worry about the scales, okay, and there it is, right? Beautiful curve there, our typical exponential curve. All right, now I just want to start it right here, and that's at 28, okay? And then it just kind of ramps up, right? And really it stops at the point 24, 113, which is apparently way above 120. All right, I don't need to get the graph exact. Okay, I just want to get the general shape. I want to mark the y-intercept. I'm going to actually write it down. 28 on my graph. All right, and that's good enough. An exponentially increasing function because the base, right, the multiplying factor, the base, is greater than 1. This thing is going up. All right, let's keep making more of these models. There it goes. All right. Now, exponential functions are easy to interpret as long as you recall what we learned about percent increase and decrease, and also what we learned about with exponential functions. Let's see what you can understand about them in exercise number 2. If the savings in a bank account can be modeled by the function s of t equals 250 times 1.045 raised to the t, which of the following is true? All right, so what I'd like you to do is actually look through all 4 of those choices and see if you can interpret what that 250 and that 1.045 are telling you about what's going on here. All right, well, in any exponential function, this is always the initial amount. All right. That is always the initial amount of flies, the initial amount of money that we put in, etc., which means that we can cross this one out and this one out as possibilities. We did not originally put in $2.50. We originally put in $250. All right. So now, how do we interpret the 1.045? Well, 1.045 is the same as 1 plus 0.045, which is the same as 1 plus 4.5 over 100, and this right here is 4.5 per 100 or per cent. So in other words, the initial amount deposited was $250, and the interest rate is 4.5%, not 45%. That would be a great interest rate. If you can ever find a bank that's going to give you 45% interest on your money, you put every cent you have in there, all right? But this thing, because it's 1.045, is a 4.5%. All right, now we can also construct decreasing exponential functions based on the percent that remains as the multiplying factor. Remember, right, when we are decreasing something by a given percent, we multiply by the percent that remains. So let's see how that's done in exercise number 3. As water drains out of a pool, the depth of the water decreases at a constant percent rate of 20% per hour. The depth of the water when the draining begins is 12 feet. Letter A, as in number 1, find the depth D of the water in the pool after each of the following times. All right, so remember the idea here is that when I decrease something by 20%, what remains is what is important. And of course, what remains when we decrease by 20% is 80%. So if I want to know the amount that's there after 1 hour, I'm going to take my original amount and I'm going to multiply by 0.80 or just 0.8, whichever one you like. Doesn't matter, they're the same number, right? So I'm going to take 12 multiplied by 0.0. Whoops, that doesn't help at all. Let's go back to my calculator. 12 times 0.80, and that's going to be 9.6 feet. Now, just like what we did before, right? If I want to know how much I have after 2 hours, well, technically I would be taking the 9.6 and multiplying it by 0.8 again, okay? But that's really then 12 times 0.8 times 0.8. So after 2 hours, it's going to be 12 times 0.8 to the second, right? I get to multiply that original depth of 12 feet by 0.8 twice because I'm reducing it by 20% twice. And again, simple enough now, right? We've got 12 times 0.8 to the second, and that's going to give me 7.68. No need to round to the nearest whole number or even to the nearest tenth here. We're talking about depth of water, so unlike a population of fruit flies, the numbers or the outputs here do not have to be whole numbers. All right, finally, for t equals 3, easy enough, I would be taking this one and multiplying it by 0.8 again, which would then be 12 times 0.8 to the third, right? I get to decrease it 3 times by 20%, or better yet, by multiplying it by 0.8. So 12 times 0.8 to the third. Enter, let's bring this thing over. That's 6.144. Okay. Now, letter B. Based on A, create an equation that gives the depth D of the water in the pool as a function of the time and hours it has been draining. All right, I'm pretty sure you can do this one on your own. Pause the video now and see if you can write down the exponential function that's going to kind of generalize what we've been doing here. All right, it's simple enough, right? D of t, nice function notation, is going to be our original amount, 12, times our multiplying factor, 0.80 or just 0.8, up to you, all raised to the t. And again, what's great about this, right? In our previous example, we had an increasing population, so the number we were multiplying by, 1.06, was greater than 1. Here we have a decreasing depth, so the number that we're multiplying by is a number that's less than 1. Now let's take a look at the graph in letter C, right? Letter C. Using your calculator, sketch a graph of your function over the interval 0 to 20, t greater than or equal to 0, less than or equal to 20. Decide on an appropriate y window and mark it on your graph. Also, mark your y-intercept on the graph. All right, well, I'd like you to play around with this a little bit because I want you to work some to get the good y window on this. Pause the video now and see if you can get a good exponentially decreasing graph. All right, well, let's open up that calculator. All right, let's go over to our graph. And actually, I think I'm going to just do a brand new document. I'm going to add a new graph. All right, what do I have? I have 12 times 0.8 to the x. Looks good. Enter, and that. Now that is a perfectly nice looking graph, but it certainly isn't a good window. Okay? Now to begin with, right, they've given us the x window on here, right? The x window in this problem goes from 0 to 20. All right, maybe we want to include a little negative, but I definitely know my x window needs to go all the way out to 20. So at least I can play around a little bit with that. I go to my window settings. Maybe I'll go like -5 on my negative x and then 20. And let's see. All right, that's looking better, right? At least I've got my x window correct, going all the way out there to 20. The problem is I can't even see my y-intercept. Now, what is my y-intercept? Well, I know, right, that this is my model. And I should know with exponential functions at this point that this number right here is my y-intercept. So I want to draw a graph that has a y-axis that at least goes up past 12. How far past 12? Well, that's a little bit more art than it is math, okay? So what I think I'm going to do is I'm going to go into my window, all right, and I'm going to come down here. I'm going to keep coming down here. Here we go. I'm going to set my minimum y to be -5. That's no big deal. And I think I'll set my maximum y to be 20. I know I've got to hit the 12, and let's take a look. And that's a pretty nice graph. You know, if I wanted to take up even more space, I could maybe make it 15 instead of 20. It doesn't matter too much. All right. I'm going to mark this at 20. I'm going to have my y-intercept at 12. And I'm going to trail it off like that. All right. I'm not, by the way, going to draw any of the graph that's out here. Why? Well, I'm not going to do it because it says graph it from 0 to 20. T equals 0 to t equals 20. Anything out here, right, is negative t values, negative time. There's nothing wrong with negative time, but the problem just said 0 to 20. I'm sure some of you right now are going, there's nothing wrong with negative time. We're not going to worry about that right now. All right, let's take a look at letter D. It's safe to cover the pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait to cover the pool? Explain how you found your answer. Wow, all right. Well, so I really want to figure out when the output of this function is going to be 1, right? So I am literally trying to solve this equation. 12 times 0.8 to the t is equal to 1, right? That's what I have to solve. Okay. Now, I'm almost a little bit worried to step back and say, go ahead and try to solve this, because quite frankly, you have no algebraic way of solving this equation. Are there algebraic ways of solving that equation? Yes. Do you know them? No. They involve things called logarithms, all right? And you'll learn all about those in Algebra 2, and I hope you all take Algebra 2, all right? But right now, you don't know a way of solving that algebraically, but you do know a way to solve it graphically, all right? And the way that we can solve this equation graphically is by putting this equation in as one function, which we already did, and then I'm going to put this equation in as another function. What do I mean by this equation? I'm going to graph the line y equals 1, all right? So I'm going to go into this thing, and I'm going to go into Menu, Graph Entry Edit, Function, f of x2. I'm just going to put in 1. Right? I'm just going to graph the horizontal line y equals 1. And then what I want is I want their intersection point, which I can see on the graph right there. It's probably a little bit more difficult for you. Let me blow this thing up a bit, right? I can see that intersection point right about there. Okay, that was kind of cool. I'm a little bit worried by what that just did. But let's use the intersect command now on our calculator. I think I'm going to move some of this stuff out of the way so it's not kind of like getting in our way of seeing it. Let's go into Menu, Analyze Graph, Intersection. All right, I want to move that a little bit to the left of the intersection point. Now I'm going to move it to the right of the intersection point. And that is at 11.1 rounded to the nearest tenth, comma 1. All right, let me just minimize this for a second. Okay, I hate the fact that there's a little hand there. I don't know why it does that. All right, so I have this intersection point. Like this. I'm going to put y equals 1 here. I'm going to draw a line here and say this is y equals 12 times 0.8 to the t, or x, whichever. This is at 11.1 comma 1. Okay, and that's because my calculator is rounding it. It's not actually that nice, but it's at 11.1 comma 1. Now notice it says, what is the minimum number of whole hours that we should wait in order to cover the pool? Now, one of the things that's a little tricky here is it would be tempting to say 11, because most certainly if you were rounding 11.1 to the nearest whole number, the answer would be 11. The problem is at 11, we're actually a little bit above 1 foot, right? We're actually a little bit to the left there. So strangely enough, the correct answer is 12 hours, right? That 11.1, because we have to be less than a foot deep. We've got to be underneath that line. We've actually got to go out to 12 hours in order to hit it. Cool though, right? We needed to solve an equation that we had no algebraic way of solving, but we could easily solve it graphically by just graphing the left-hand side, which we already had graphed, and then graphing the right-hand side as that horizontal line. All right, let's keep working. Okay, so let's take a look. Exercise number 4. Which of the following equations would model an exponential quantity that begins at a level of 16 and decreases at a constant rate of 8% per hour? All right, well, take a look at these and see if you can figure out which one is the correct choice. All right, very important, right? We've got an exponential quantity that begins at a level of 16 and decreases at a constant rate of 8% per hour. And of course, if it's decreasing at 8% per hour, right, that means that there's 92% left each time. which means my exponential model, right, that is always my y-intercept 16 times my multiplying factor 0.92 raised to the x. Not exactly the same variables, but that's okay. Q equals 16 times 0.92 to the t. Oftentimes, by the way, if you haven't noticed this yet, when the input variable is a variable that represents time, minutes, hours, seconds, whatever, we'll oftentimes use that input variable as t, or we'll represent it as t rather than x. All right, one last problem. Now, sometimes we will need to decide whether we are dealing with an increasing or decreasing model based on the description of the scenario. So let's take a look at exercise number 5. If $350 is placed in a savings account that earns 3.5% interest applied once a year, then how much would the savings account be worth after 10 years? Okay, well, hopefully you can look at this problem and figure out what the model is and how to use it to figure out what your savings is after 10 years. Pause the video now and see what you find. All right, well, let's build the model. Now first, the fact that it earns 3.5% means that it's going to be an increasing model. Specifically, what would the model be? Let me use S for savings as a function of time. Well, it's going to be what we started with, 350, times 1 plus that percent as a decimal, 1.035 to the t. Therefore, if I want to know how much my savings is worth after 10 years, I'll just have 350 times 1.035 to the 10th, and now this is just an issue of hitting the right buttons on the calculator and having the calculator still work for me. All right, let me go back to my calculator. There it is. There's my calculator. Not that I can see it. We've got 350 times 1.035 raised to the 10th. That's going to be 493.71. And that is choice 4. That's what's known as compound interest, right? When interest builds upon itself and you earn a lot more money than you'd think you would. Okay, let's wrap this thing up. So today, we put together a lot of things that we've been doing for the last few lessons, right? We put together our knowledge about how to increase and decrease quantities by a certain percent. And then we put that together with our knowledge about exponential functions to be able to build exponential functions based on percent increase and decrease. We'll continue to work with these type of models as we go on through this unit and through this course. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.